just about the electroretinogram itself, I'm going to be talking about the electroretinogram from its basics. So this is what we could record as a mass response to retina to a luminance stimulus. And we need to know more details. All of those details in the entire technical terminology is there in the ICEF website, which is mentioned over there. And I suggest anybody who really wants to do any amount of electrophysiology should be familiar with these standards, because that's the standards that are maintained over the world. The method for pediatrics, I put cheat over here a little bit, and you actually asked me to speak about infants, but I'm going to talk about a little older children and then come down to the method. But the method varies a lot from an adult ERG to a pediatric ERG. We need to modify our methods quite a lot. For one, there are many different types of electrodes that we use, but the one that we've now fallen back on is this one, the gold foil electrode. The gold foil electrode or a DKL electrode is probably the least traumatic electrode that can be used for electrophysiology in pediatrics. And we tend to prefer that. In the days when we were not using the gold foil electrode, we were using the jet electrode. And this is an example of a child actually accepting the jet electrode without much complaint. But halfway through the test came back to complain. And then we had to induce the child under anesthesia for further testing. So, to avoid anesthesia, we've now fallen back a lot on the gold foil electrode because it's successful in that. That being said, the burinalin electrode is really a fantastic electrode to give you a quality recording. And the reason why we don't use it is that not every child is as cooperative as this one with the burinalin electrode. So the basic principle of the test is that we show a luminance stimulus, get a response from the retina, and that retinal response can then be translated into a waveform. And that waveform will tell us a little bit of information about the electrical responses that are coming from inside the retina. Now, if you want to study that in detail, we have to look at the layers of the retina. So when you look at the layers of the retina here, you'll notice that when you shine a flash of light, the response moves from the photoreceptors to the middle retina and then the inner retina. I can show you that again like this. And when we put that into a waveform, you actually see that the photoreceptor response is the A wave over here, which is caused by photoreceptor transduction. And then the middle and inner retinal responses are responded to with the B wave that follows after that. There are other ways to look at these electrical responses. There's something we call oscillatory potentials, which looks mostly at the middle retina over here and the inner retina as well a little bit. The way that happens is they use electrical filters to filter out what comes from only the middle and inner retina and not pay attention to the photoreceptors at that point. So the way we progress with testing is that we first look at applications, and the reason why we do that is we get all of the rods and cones into their basal resting state. And when we do that, even when we shine a very, very low intensity stimulus, only the rods will respond. Because the rods respond to low intensity illuminations. And when we do that, the type of response that we get from this wave is something like this. We don't really see an A wave with the dark adapted responses. We see only a B wave if we shine just a light that's just lighting up or something like that. Then, following that, we then light adapt the patient. When we do light adapt the patient, when we're done with the scotopic test, all the rods will then become saturated. And when they become saturated, the only photoreceptor that will respond will then be the cones. And when the cones respond, then we get only that cone wave, which is recorded something like this. We can also elicit the cone responses using something called the flicker. We use a curtain lux flicker, which is fast enough for the cones to recover, but not fast enough for the rods to recover from the flicker. So when that happens, only the cones would be recorded over there, and the response that you see from the flicker would be something like this. So this is what a normal electroretinogram will look like. In a normal electroretinogram, we're measuring the A wave, we're measuring the B wave, we're seeing when the A wave occurs and when the B wave occurs. What I'd like to point out over here is this blue line over here is what is the machine, is what we've calibrated as normal for our machine environment. This would have to be calibrated separately for each individual machine around the world. And when we do that, only then can we make comments like this, which is that this wave is actually long. This A wave reduction that you is not a reduction, it is like fixing within our 95 percentile deviation that we see with our, and this is probably just the edge of the deviation. So such comments can be made only after you calibrate the machine or log particular setup. This, of course, I don't have to introduce you is how the normal retina would look from a normal retina calibrated retina and the corresponding machine. I'd like to elicit the usefulness of electrophysiology through some examples over here, especially with night blindness. The various causes for night blindness include these that are listed here, but the ones that I'm going to talk about are only a few. This is a problem called CSMB. I think if you go to my slides here are out of the picture, but basically what this shows you is that there is an A wave over here that was normal along with the A wave of the blue line over there. But then all of a sudden you don't get a B wave being formed. So when the B wave does not get formed, you get a flattening out of what is called an electronegative ERG where the A wave is higher than the B wave. Something like that is typical of a situation where the middle retina is not functioning well, but the photoreceptor transduction is not functioning. This wave over here, since it's being done in a child, this does look abnormal with the freezer that is next to it. It shows you that the phone wave is rather normal. This is something else that we see with the CSMB, the simplification of the oscillatory potential. And this is the fundus picture and the OCT of the CSMB, which you will not be able to make out much as abnormal in this situation. And this is how we see the autofluorescence, and I'm showing you the autofluorescence with the autofluorescence in the CSMB with relevance to the next case that I'm going to present. Because in this situation, we get types of CSMB, yes, which do not have a large, let's say, an electronegative response. We also have such types of CSMB, although they're much rarer, because in those situations, the problem is actually in the photoreceptor transduction of only the rod, which could also occur in micronegative issues and other rhodopsin gene issues. But in this situation, we were really wondering whether this is a CSMB or a rod cone dystrophy, and the answer was not elicited by the electrophysiology itself. You see here this fundus picture and the OCT looks normal. So what we really looked at was the fundus autofluorescence, which will show us a halo or ring like this, which tells us that this is actually a rod cone dystrophy and not a CSMB. And this is a rod cone dystrophy that this might be an early rod cone dystrophy that you usually see in pediatrics, but you might not see in adult practice. This is a more typical rod cone dystrophy, of course, in its advanced stage where most of the areas are flat. And this is how the retina would look here. If you look more in the periphery, you start seeing more of those bony spicules there. But this is how it is. And with the OCT per se, you can notice that the photoreceptors that are present are probably present only in that area. With that, I'd also like to move on to how we elicit electrophysiology to give us information in nystagmus. And these are the causes of nystagmus, but I'm going to be talking only about two to elicit the example here. And the first one is the cone dystrophy, and as you can see over here, the rod waves over here, or the scotopic waves here seem rather normal, and so does the oscillatory potential. When you come to something that's lighted after, this is a lighted after wave, and this is a flicker wave, you see a large reduction in the amount of wave response over here. And we know that there's something wrong over there with the cone system of photoreceptors. And when you look at the fundus again, you'd see a rather normal fundus with a rather normal and that's something that we want to elicit, that electrophysiology can probably bring such things out in these cases as well. Leber's transcendental amaurosis is defined by its black ERGs. What I'd like to point out over here is also while recording the retinal responses, you do get electrical noises in non-ideal situations. This was taken under general anesthesia where the operation theatre's earthing is not as good as the earthing in your electrophysiology room. So in that situation, you are prone to develop some noise situations. And I think in our operation theatre, there's a special situation in that whenever the elevator of the building goes up and down, the noise increases. So we have to sometimes retake those tests when we see the noise. But this over here is particularly noise and not anything else. So these are things that you learn to recognize once you are actually doing a lot of electrophysiology. And the Leber's transcendental amaurosis in this child was a situation where the fundus also looked normal. We didn't have an OCT for other anesthesia. So in conclusion, electrophysiology is actually an essential tool to detect nowadays we're talking about genes and gene therapy, so we really need to have a clear phenotype to know what type of disorder that really is. And specifically with pediatrics, it's useful with explaining nystagmus, night blindness, and some physiology. Thank you.